So hello and welcome to the Code Maven meetup group. And if you're watching the video, then the Code Maven YouTube channel. My name is Gabor Sabo. I usually teach Rust and Python and help companies introduce these languages or introduce testing for these languages. And I also organize both the Rust and the Python meetup groups here in Israel. And I also have this Code Mavens group where I try to organize presentations both in Rust and in Python in English, in Zoom, so we can reach all the international community, and we can also invite people. If you look at the history, you can find all kind of other videos from other people about all kind of interesting subjects in these two languages. With that said, I am really happy, Leon, that you agreed to give this presentation. I think this is the third time you're already giving this, or sort of.
Yeah.
But this time it's in English, so we'll have it also for the international community and recorded. And thank you very much, everyone, who joined us. As I said earlier, you can feel free to ask questions in the chat, and if you don't want to speak up. And that's it, I think. Leon, it's now the stage is yours.
All right.
Share your screen. You can talk without sharing the screen, whatever you like.
All right. All right. All right. We're there. Right. So, let me just share the screen again. Right. So, you guys will be able to see my screen very soon.
Yeah, we see the embedded summer camp.
Okay. 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 Very good. So, right. So this meetup was created as a part of three separate meetups we have arranged in our company called Abra. And this was the specific one we're talking about right now is the Rust in embedded systems. And it was the second one. The first one was Linux kernel development, which was not related to Rust at all. The second one was the Rust in embedded systems. And the last one was Rust in Linux kernel. This series was quite interesting for me to prepare and to present, and I hope you'll find it at least a bit amusing. Right, yeah, first of all, my name is Leon, right? That's enough. You know, we the Rust people, we clearly have some issues, right? And you will, I guess by now you already are aware about our little problems. But you know, that's why we're here today. So I hope you'll enjoy it. We will be talking about Rust for embedded, and we will mention how Rust for embedded systems, for bare metal embedded systems, is not the same as Rust for, you know, when you develop in user space, like Linux, Windows, whatever. We will mention the fact that Rust provides your gives you or lets you develop in a full, it's very supporting ecosystem for embedded and specifically for bare metal. We will be questioning just a little bit Rust versus C and C++ in the embedded, just to touch on that because it's hard not to. What we will not be doing today, we will not be learning what embedded development is. I hope that you guys have any, well, just any sort of idea about that up to now, and we will not be mentioning concepts like serial port and LEDs, LEDs switching on and off and so on. right? I assume that you are aware about these things. And we are not going to be learning the Rust language. It's not about learning Rust language. I hope you will see what the presentation is about. There are not many slides here. We'll just speak very quickly about a few slides here, like 3, 4 slides, and then we will switch to a hands-on demo, which has a little issue today because there is one thing that's not working for some reason, but we will get over it. Right. So let's go ahead. What are we? Well, I cannot say we're all familiar with that, but many of us are well familiar with it, with the good old bad old days when you were quite locked with development under a specific platform and a specific IDE and a specific debugger and whatever. Zilog is a good example. I used to work with it once. And yeah, so we had an IDE just for it, special debugger, probe, and everything is quite unique for this platform. So yeah, so it's all about the ICs, the chips eventually. So the chip was from Zilog and the IDE was developed by them, and the compiler and the debugger, everything is just, very custom. And now we have Rust. And this is very, very different from C because, well, we have the next slide, so why rush? First of all, we will be moving from vendor lock-in to freedom. We are really capable of developing whatever we want without um, any code supplied by the vendor entirely. We will use any IDE that we like. I'm used to work with VS Code, but you can use any IDE of choice. You don't need an IDE. Yeah, you can use just the code editor. For the hardcore guys, you can do everything in Vim. And what's good about Rust compared to the bare metal C programming? It's the power of modern language in embedded programming. It's just incredible what stuff you can do in bare metal if you know, if you if you're used to bare metal programming in C, then the switch to Rust would just knock your mind off. Yeah, and why Rust? Of course, unmatched safety, concurrency, and what about the performance? Well, we really need to talk about it because that's one of the main questions people always ask about, why use Rust and not C, not C++ in embedded development. So, and many times everything boils down to performance. I will give you the tools to measure your own performance requirements. So let's look over here. You have the, I'll try to make it slightly bigger. You have the benchmark game, right? This is under Debian, okay, debian.net, benchmark game. You can find it easily on the net, okay, no worries. And you have certain comparisons of Rust versus other languages. So let's take C, for example, right? You have the comparison to GCC, and you have different algorithms here. Everything is very, very, open. So if you click on the specific algorithm, you get the all kind of measurements and you can get to the algorithm itself, the implementations, everything is here. It's all it's all open source and available. So when you compare Rust to C with GCC, for example, you can see the the different runs here, and you can sort it. You can do a lot of things here, but eventually you will see that Rust is not better than C, and C is not better than Rust, depending on an algorithm and on the tests performed. In some C would be quicker. In some, Rust will take the first places. It's just, it's all right. They are quite the same eventually. So no need to worry about performance. The performance is, how would you define it? I suppose it's as good as it gets, at least, using modern compilers and systems. You can instead compare it to the Clang. Once again, the picture doesn't change much. So feel free to go to this site and check it for yourself. I will not be teaching you what's the best for you. You can compare it to any language and with different algos and whatever. So enough with that. I suppose it's quite clear by now. Why does it start again? Okay, sorry. Okay, so this is about the performance. Talking about safety, concurrency, and whatever, I guess that by now your Rust shines on these sides and way, way better than C. So if the performance is the same, so why choose any other language? Oh, yeah, by the way, this is Ferris. Just so you know, this is the mascot. His name is Ferris. Any idea why he's called Ferris? That's very simple. Pharaoh, like Rust, like whatever, programmers' jokes. All right, so what and how the bare metal programming is different? Well, eventually, when you write any program for C, for any OS like Windows or Linux or whatever, eventually your code will swap to using C interfaces because the operating systems, not all of them, but most of them, are written with C, and your code will just run C code eventually under the hood. Here is an example using the foreign function interface. This comes from the Rust. It's just a random example. Rust lang, Rust tree master library std src os Unix fs. So this is a file system library for Unix, and this is just one function from it, make dir function. What does it do? It simply calls the libc make dir on this machine. This is quite clear because these things are implemented on the libc level, and everything boils down to that. There is certain question that one may ask: if it all boils down to C, then why use Rust? Well, if you can write big apps with lots of business logic and feel safe on memory issues and everything else Rust helps you with, then I think you've done a good job here. Anyway, foreign function interface is an interesting topic to read about. FFI, you can find it easily on the network. And by the way, Rust is an open source language. Just try to find the code for make dir in libc. It will take you some time, I promise you that. It's not that easy. With Rust, you just get there almost immediately with any search on the network. So, yeah, so you're programming in Rust. However, you're getting to see interfaces on the OS ABIs. The Rust for embedded is very different on these regards. Well, once again, when I say Rust for embedded here, I mean Rust for bare metal embedded systems, all right? So as you can see at first, you see, well, you guys, I don't know, some of you may have experience with Rust, some not. I will explain some basics, don't worry about it. So you have the no std and no main. Why is that? Well, first of all, there is no standard library. There is no standard library under bare metal programming. You don't have any special library behind everything. You don't have the libc or stuff to help you with. There are certain standard stuff. There is a small standard library built into your code now when you compile with no std, but these are just basics. And no main, because you feel free to select your entry point. For example, here it's called my main, and it has the entry syntax here that marks it as entry point for this function. So when it builds, the linker will arrange the start of our code over here. So what you see here is some basic code for a bare metal program in Rust. Apart from the main, you have the core panic info stuff, which will be used for this function because we need to provide the panic function. This is the only function that we really have to provide apart from the entry function. And why do we need to provide panic? People familiar with programming under an operating system are used to error handling, to all kind of mm, all kind of failures that are treated, whether in well, we are talking about runtime stuff right now. So at runtime, your program can fail in different ways, but in a bare metal embedded system, you don't have this luxury. You need to handle your panics by yourself. And when your code is about to panic, you need to provide it a handler to go into. And I'll just give you just a thought, why is this here? Why the inline never for the panic handler? Any ideas? Why cannot this function be inlined? The reason for that is that this function will be called by a pointer. This function sits somewhere in the memory, and in case the CPU performs some illegal function, like dividing by 0 or any other failure, then it will just jump over to the panic function. Now, inside panic function, it's up to you how to handle it. It's bare metal. You have no OS to look after. So it's up to you. You can reset the platform, for example, or you can just do nothing and get stuck in the loop, whatever you want. So this here is a very basic program for the Cortex-M stuff. Now, how the things work with Rust for bare metal programming, with embedded Rust for bare metal. First of all, you have the hardware, right? We all know LEDs. And how do you control this hardware? Well, you can use direct register access. This is an example. You use unsafe and you write volatile. And this is the address, right? And then you read volatile, PTR read volatile from the same address. And then you perform an operation on it just to light up the relevant LED. And then you write it back. So you read the value, you modify it, and then you write it back to the memory. To do that, you need to understand very well what you're doing, because this is just an address. It's just a register in your MCU. So you need to understand very well what you're doing here. You need to read the data sheets and figure out everything for yourself. The next level, just above it, is the PAC, the Peripheral Access Crate. This looks very different. First of all, you use the relevant PAC. In this case, I gave an example for an STM32F4. This is all open source and everything very accessible. You can check out the code inside, whatever you want. So there you apply to GPIO A, number A, which is the one of the GPIO sets. And then you have the output data register, and then you modify it, all right, which is a method in SVD to Rust, which we'll just mention in a second. And then you just use the ODR5 in this case, and you clear a bit. This makes more sense than what we've seen below. Now, what's the SVD to Rust? Well, most MCU manufacturers provide SVD files that define the whole usage of their GPIOs or the pins of the MCU, and you can use the SVD to Rust tool to create the packs. Okay, so packs can be created automatically, mostly by just receiving the proper SVD file for the platform. So if you have your own, like you developed your own silicon, or just have something that is not currently supported, as long as you have the SVD file, you're okay. You can get more information about it in SVD to Rust. Just type it on the net and you will find out. So this is nicer, but we can do better. One level above it is the hardware abstraction layer, HAL. We all know this name. And the HAL is way more convenient for us. As you can see here, we use the HAL, and we have the sample usage like GPIO-A, PA5, which was the ODR5 over here, and maybe probably number GPIO number 5 over here, into push-pull output. Okay, so we first configure it to push-pull output, then we set it to high, and that's it. All right, so here, this is very, very straightforward, very convenient to use, and you have it all in the relevant HAL crate, like STM32F4XX HAL. But then you have the board support packages, which are fantastic. The difference between HAL and a board support package is that the HAL allows you to work with the MCU. So you select the MCU and then you use its HAL. But board support packages is clearly for a board. So
Leon, sorry to interrupt you. I have a question, if it's okay. Is this layers? Can you hear me?
yeah, I'm with you.
So are these examples really related? So meaning that there is the lowest level the direct register access, you have this hexadecimal number.
Mhm.
Is the ODR actually correct? The ODR corresponds to that, or so is there a name for basically
Yes,
for that?
yes. Under the hood, it works exactly like it's shown here. All right. Eventually, everything boils down to these commands, but they
Okay.
are just wrapped in layers of wrappers that allow you to use them in the easiest way possible.
Okay, so basically what you can see on the pack level operation is basically doing the same reading and shifting and writing back
Yes, exactly.
with the clear bit. Okay.
Yeah.
Okay, thank you.
So the difference between the HAL and the BSP is because BSP is about the board. So the actual board, like this one over here, this is a board. It's a specific board that you can get and use. So if you have evaluation boards, many of these evaluation boards, like the Nucleo over here, you have the BSP available for them. Now, why is it better to use the BSP eventually if you're using an evaluation board? It's because here, for example, we can define an LED. So when we define an LED, and of course we configure it as appropriate, then you just have the on method for the LED because we know that this is an LED. It's not just a GPIO because we know that behind this specific GPIO on this specific board, we absolutely have an LED. So we can configure it and just use the specific LED with just an on command. And it makes the life very easy. And also, if you have your own board, if you develop your own board, then you can use some basic or some similar BSPs to define your own BSP and work, like a king with this board, very easy interface. So these are the layers of working with um, these are the layers of working with Rust with MCUs in bare metal. Now, you know, uh, um, I use C, the C language, in embedded development for too long. And then when I started, considering this meetup, I just did a test. I just went to the internet, on Google and wrote cross compilation setup in C. And the first thing it brought me to was Stack Overflow, cross compilation requirements. I have some basic knowledge about compiling with C, need to get a couple of generic cross compilation questions answered. In my case, I'm trying to whatever and this and that. And there were lots of sections like that and no real good explanation. If you do the same in Rust, you immediately arrive to the right place, to the right website, and to the right page that explains you exactly how to build everything you need. And this is just fantastic. This is why Rust is a modern programming language, unlike C. We can talk a lot about that, but we will not right now. Still, the picture is clear. I clearly feel the difference here. Yeah, this is just some fun poster I made for explaining my feelings. Yes, C is quite confusing at times. Rust is way more straightforward. So you can be ready to go, to Rust in 5 minutes. Maybe less. It's all up to you. You install the cross compiler and set up a project. That's all. So Rust up. target add, you add your own target, depends on what you work with. Then you create the project. Then you go into your project. Then you cargo add. For example, in this case, it's Cortex. And there are different targets. We will mention RTT very soon. And that's about it. You're ready to work. Now you code it, you set it up for the target, and then the fun part begins, because unlike with C or any other language, well, most of other languages I'm familiar with, you check it, build it, flash it, debug it, and even more stuff you can do with it, like RTT it, and so on, just with one single command. It's cargo embed. You don't have to use it, but this is a wonderful command. And once again, I'm mentioning this is a great ecosystem to start working with embedded development with bare metal. It's cargo embed. You specify the target, or you can specify it in the configuration file, and that's it. You just type cargo embed, and it's already there. We'll see it in a second. So cargo is really, I really believe that. It's the marvel of modern development. It's incredible. It allows you to create new projects very quickly with Git built in. You add and manage crates and utilities. You have simplified, efficient builds because, well, when you use it, the integrated testing framework inside automatically generate the documentation you want. Seamless embedded workflow, very easy. Manage multiple related packages. Cargo is a fantastic tool, especially for the beginners. It allows you to do everything quickly and very, very efficiently. You really should read into the cargo abilities because, well, I do believe many of you have used cargo in past, but many of us Rust developers are not quite aware about the whole list of things you can do with cargo. It's very nice reading. So before we jump to some code, any questions? Oh, that's nice. Oh, that's from the meetup. We had refreshments there. Because I'm going to show you some code. By the way, you can check out all the examples here because we don't have much time for the examples, but you can use this repo I created just for the sake of this meetup. I will, here is the chat. I will put it right here so you can access it. All right, good. So we have this code over here. And let me see. All right, so we have the first example here.
Can
Now
you
I'll
enlarge a little? Sorry, can you enlarge a little bit the font?
no. Eh, of course I can. Just a second.
It's embedded. You can't enlarge the font.
All right. So we're good. All right. So let's see. So this is the first example. I believe it would be the most important one. We have the main here. So as we said, no STD and no main. Then we use Cortex M, and we don't really use it. Why do we do this then? For default critical section implementation, when we are not using the microbit crate, we will be working with this board called microbit. It's by BBC. You can check it out. You have some. I believe you even have links in the repo. This is just a board with a few LEDs and stuff on it. and it's very easy to use, very cheap, very nice for beginners. Yeah, so we have when we are not using the microbit crate, and we don't here, so we are not like using HAL or BSP, but we are using Cortex-M. So we are applying directly to the CPU of Cortex-M. We're using the entry point, and we have the RTT. The panic RTT target simply brings us the panic section that we don't need to create it manually. It does it for us. So when you use this panic, then it will just add the handler function for you. And then RTT, whoa, I don't remember the abbreviation, but RTT is just the prints. This is a protocol by Seger used for debugging over different debuggers, and you will immediately see how it works. So we have our entry function. We have the RTT init print, so initialize it for printing. Print a hello message to the RTT, just like our print line. This is the function. And that's it. And then we're stuck in a loop forever. Now, how do we actually build it and work with it? It's quite easy. I go into the example1 directory, cargo, embed. This is everything we need to just build it and run it. It built it, flashed it, and ran it just for us. So we have hello from microbit, and this is the output of the RTT interface. As easy as that.
It's connected with a USB, right?
Yeah, it's connected with USB, and it creates 2 serial ports on the system. Okay, so this is all going through a serial port. Maybe you can even see the port over here. No, you cannot. Whatever. Right, so now let's take something more interesting. You know, we are all embedded guys. We like seeing LEDs on and off, right? So here we have the matrix, and now here I already start using the microbit crate. This is the BSP. Okay, so it allows me to use the board in a very, very easy way. For example, well, you can see just some sort of array over here. And this is a kind of irrelevant function. We will not go into it. But then what do we do here? Just look how simple the code is. Board take. Okay, so we initialize the board. Then we initialize the timer because we need a timer here. So we use the timer 0 of this board. And we need the display. The display in this case, because this is BSP, so it has a display for, as you can see here, you have the LEDs, a matrix of LEDs. So now you just loop through the matrix just by creating display show, and then and that's about it. You just have the display show function that you display the array. So let's run it. No, not here. cd x example2 cargo embed. All right. Now what do we see here? Hey, this is the best moment in my career. All right. So we have successfully created a LED carousel. Now, I want to show you just a bit inside of how the things work. What files do you need to use to make this all happen? Unlike with simple Rust that you use with an operating system, here, apart from your main, you have a few things. Let's start with the standard things, cargo.toml. It just includes the libraries and everything, the crates we have here. Everything is quite standard. All right. Don't forget about the features using Cortex-M, critical section, inline asm, and so you need to get them in. But then you have two additional files which are very important. You have the build.rs. The build.rs script is quite standard. It's not special for every project. You don't have to change it, but you might want to change it. Eventually, I will not just go through everything here. It's quite clear, but not very obvious from the start. It simply makes sure that your linker will take this linker script. Because as usual with embedded development on MCUs, you need to specify some initial data for the MCU to run. So here it's quite simple. You have the flash memory and here you have the RAM. Very easy. And the build.rs simply makes sure that this is the file that's used by the linker. And the last thing, well, not the last one actually, but let's look at it. The embed.toml. This file is actually specifies everything you do with cargo embed. The cargo embed command deals with this file. So you can set up the default protocol here. Like currently your probe is single wire debugging. You can also specify JTAG, it depends on your debugger. You just specify it over here. Then you have the general settings for the target. Like, for example, you need to specify what chip you're using. So in our case, this is the Nordic chip, NRF, whatever. You need to get this information from the chip you're using, right? So you can specify chip models. The default reset operation here is that you can halt after flashing. Why is it useful? When is it useful to halt after flashing and stop the program from running? It's during your debug. Okay. And then you have the default RTT, which is either enabled or not. For example, in this case, I don't use RTT at all. There was no RTT in my code, any of it. So why did I enable RTT anyway? Because, and why do I initialize it anyway? Because for debugging, I still use RTT target and yeah, the panic target. So if I get any panic, it would print me something on RTT. So I will know I have a panic in my code. But I can drop it. Okay, so for example, if I change it here to false and I build it again and run it, you will see that RTT is no longer enabled on start. Okay, the board is still running, of course. That's it. You also have the default GDB, and note this, it's enabled. The GDB is enabled here. And you can specify the port. Let's get to GDB, no worries. And default flashing, of course, you can enable the default flashing, but you can, if you have a different flashing algorithm or program, you just specify it here. No worries at all. It's all very configurable. Now, let's look on the GDB stuff. So we are here, and I will quickly start the debugging. So I will just copy and paste some commands to not annoy you. I'm running the GDB multi-arc with my target executable. All right. So I'm inside GDB now with my target. Now I want to connect to my remote, which is by default on this port.
Could you enlarge the fonts here too, please?
I don't know, maybe. Let's see. Yes. But now I will need to, yeah.
Thanks.
All right. And now I can I believe it does it by itself, but I source the GDB in it, doesn't matter. I will just configure the dashboard a little bit. Okay, and let's have a, didn't I? That's kind of strange. Okay, no, wait. Yes, let's start it again. Oh, yes, right. So that's the problem. Let's see. Where am I? Target. Okay. Debug. Um, hmm. Okay. All right. So where were we? Mm, breakpoint. The program is not being run. What's going on? This is what happens when you try to show something quickly. Exec format error. That's strange. Let's try something else. Something is wrong about it. Well, I will not continue with this direction because I will waste all your time and I still want to show you stuff. But generally speaking, debugging is quite easy because you have the debugging built in already. All right, so you can simply connect and debug your code. And it's all very convenient because you don't need to even add another line over there. One more thing to mention is that in config.toml, you can specify how to work with your specific configuration. Like in this case, I've configured that all ARM and target OS and so on use the linker script, the specific linker script. And that's quite easy, or you can provide your own specific target if you want. Really up to you. So these are the main files that you have here. We mentioned the embed.toml, the most important file for cargo embed. You have the cargo.toml standard and the build.rs, which selects the linker script and the linker script itself. That's everything we need to get going, and it's all available on the net. Just another example here. Let's say cd. Let's take example for the accelerometer, cargo embed. Yep. So now we have the values from the accelerometer on this board. So you can see the values are changing in the 3 directions. And yeah, and how you achieve this thing quite easily. You have the code right here in front of you. So you have the from microbit, you get the TWI interface, the UART interfaces, timers, and everything. Then, in this case, you initialize the board itself, as usual, board take. Then you initialize the timer. You have the serial, UART new. As you can see, everything is very straightforward here, right? It's the simplest thing you can think about to initialize a serial interface. And then you set up the I2C interface, the two-wire interface, right? Also, as you can see, very easy. You supply the frequency, and that's about it. And then here, in this case, it has the sensor called LSM303, and for which we have a separate crate, which is a totally unrelated crate, but it provides us access to the sensor. We initialize the sensor, we set the accelerator mode, and so on. And then we delay for 50, we sleep for 50 milliseconds. And then we have the acceleration. We are reading the acceleration in one command, one simple command over I2C. And that's about it. We write it to the serial line, and then we print line it as well. Now, I wanted to show you the prints from the serial line. However, it seems like I have some issue here at the moment, because when I connect to the serial line, I see nothing. And that's quite weird. I don't know. ACM0. This is the interface, but I see nothing on it. So I think I know why. I think I know why. TTY ACM0. Sorry. Aha. I think I know why. TTY ACM0. And then I think it was 1200. Let's see. Okay. Oh, hey, I got it running. So it was configured for a different baud rate, or a wrong baud rate. So you can see that now it prints to the serial interface connected over Minicom, and then you can also see it over here. And I closed it, so suppose I need to rerun it, but whatever. Yeah. So in this way, as you can see, printing to the serial port could not be simpler than with Rust here. And I remember my initial projects in C with embedded, with ST microelectronics MCUs, and with Zilog and such. It was a nightmare. Here, it's very easy and straightforward. So my my point in this presentation, because we need to wrap up, the main thing I'm trying to show here is that, first of all, that Rust is a very modern language and ecosystem for developing for bare metal. It's very convenient. It's very mature. It's not like it's something that you need to, you know, spend your nights on configuring. It's mature. You just install it and run it. It's very straightforward. Moreover, if you need, in my view, if you want to begin working with bare metal programming today with MCUs, I think that there is no reason to choose C over Rust at all, because Rust and Cargo will provide you everything you need to get going, and in a safe, memory safe way. So why bother even dealing with C and whatever? So if you have a new project for bare metal machines, there is absolutely no reason to choose C over Rust. That's about it. So Gabor, I'm quite done. I didn't show everything, but we're out of time. You guys can use the repo to check out the rest of the things.
Okay, so I'll first of all thank you very much. I just checked. I have this microbit that I bought like a year ago, and I still didn't do anything with it. It's version 2, so I'll have to see if this code. I see that in
well, this for version 2, as you can see over here, I think I put it here. Yes. So over here, you can, we work for version 1, 1.5, you use with this one. Well, the version 2 works with 7, V7.
Okay.
That's the difference. And by the way, you can find a lot about it on the internet. It's all there. You just type in. Oh, by the way, I wanted to even show you how it works. You see, you go into Rust for embedded, and you reach the embedded Rust book. I really like the documentation in Rust for embedded, because when I started with embedded programming, there was no such thing for C. There are plenty of C books, but nothing close to stuff like this. So you have the embedded Rust manuals here for everything, whatever. And then you have the bare metal Rust section, which is very specific, with all the installations and explanations about how to set things up for different operating systems and so on. And then, for example, the discovery here section, it's all about specifically about the microbit. All right, this is everything here in discovery is about microbit. And here is just another example of working with STM32 specific board. Everything is just like with all the examples and everything, very clear, very straightforward, and so on.
Excellent. So thank you very much. If anyone has any questions, who wants to still ask it during the presentation, but we didn't have throughout the presentation. Maybe you have something now, then do go ahead and ask. If not, then we are going to shut down the recording, and then you can, because you are here, you have this privilege that you can stay around, and then we can have a continue the discussion. If you're watching on the YouTube, then you have the privilege to click the like button and follow the channel. And so, Leon, thank you very much for this presentation, and thanks everyone for attending. And so, hope to see you soon at a different presentation. Bye bye.